not as similar as people like to think we are. Although cells have common components, they come in a variety of shapes, sizes, and functions. And of course, we know there's lots of different types of cells. Cells might look very similar, but do very different things. Cells might look very different, but do very similar things. But they do have a lot of stuff in common, a lot of stuff that makes up the inside of cells. Basic cells. There's a little bit of difference between the size of the ovum and the size of the sperm. The sperm is actually much smaller than the egg. But you get the idea from looking at this picture. Also, this is, the egg you cannot see with the naked eye. This is microscopic. We're just going to think you can see an egg. Nope. Okay. All right. Certainly by now in your careers, you realize that we have a nervous system. And the nervous system is the system that takes in information, makes a decision, and sends out information throughout the body very, very quickly. It's the fastest way to move messages around the body, the nervous system, lightning fast. And then, of course, we have a cardiovascular system to move blood around. We have a liver that does over 500 different things. We have kidneys that filter and do some other things. We have a pancreas that does something else, a spleen that does something nobody even knows. I'm just kidding, you know what it is. An appendix that does something else that does do something, don't listen to it. We have all these different parts that are doing very different things, but doing them all for the greater good of the organism. The cells are very similar, except cells don't have hearts and brains and livers and things, or at least not as we would recognize them. But they do have organs, but they're small organs, so we call them organelles. That makes sense. And the cell, of course, is surrounded by a selectively permeable membrane, or sometimes when we say semi-permeable membrane. In other words, it will allow some things to get through easily, but not other things. It is selective. It is semi-permeable. So, some things that cells have in common: a nucleus, the brain of the cell. You'll find a nucleus in most cells in the body. But not all cells. In fact, if I was to ever ask you what cell, well, for right now we'll say the red blood, the mature, let me rephrase that, the mature red blood cell is the cell that we would not find a nucleus. Now, the nucleus is where we keep our genetic material. This is where we keep our DNA. This is where we keep the directions. So it doesn't have a nucleus. It doesn't have those directions in there. That's why if there's a problem, the red blood cell can't really fix itself. Can't really last very long. We have a lifespan of a red blood cell about 120 days before the spleen says, your time is up. But that's okay, because we make about 1 million red blood cells a second. That's a lot. No wonder you're tired. We see these common organelles. Most cells have a nucleus. Most cells are going to have cells have to have cytoplasm. That's the sticky, gooey interior. Cytoplasm is made up of mostly water. Cytoplasm is mostly made up of water. So we have cells that make up all of our tissues in our body. Their cells are mostly made up of water. And of course, our blood, almost half of our blood is water. 90% of, 55% of blood is liquid, the plasma. 90% of that, give or take, is water. That's a lot of water. Cytoplasm It's going to have dissolved gases in it. It's going to have proteins in it. Of course it's going to have proteins in it. Proteins are going to be the thing that helps to buffer the inside of the cell. It is going to be the most potent which is the inside? Intracellular buffer. Intra is inside the cell. Inter is between the cells. So if we're talking on the outside of a cell, the most powerful buffer is going to be bicarbonate. If we're talking on the inside of the cell, it's the proteins that are in the inside of the cell that's going to act as the buffer, so it's not too acidic. If it was too acidic, we'd have damage. Damage is not good. The cell membrane. The cell membrane is a fluid membrane. Now, this is something that is hard to get a grasp on, because for the most part, when you think of your organs and you think of solid tissue made of cells, you think of a solid cell. But actually, the membrane of a cell is fluid. It's always in motion, which means these doorways that can be there to allow glucose in can change their position, but they can change whether or not they're in that plasma membrane at all, which is why we'd have somebody like insulin come along and help to get it. So the cell membrane, it's not as simple as just being a wall, but that's how we're going to describe it, similar to a wall. Cell membrane. Cell membrane helps to determine the cell shape. Some cells have to be rectangular, some have to be round, some have to have little projections off of them, called cilia. Some cells have to have the ability to change their shape. So that's going to be based on things like cholesterol in the membrane. But that cell membrane is going to help determine what shape that cell should be. It's also going to determine what is allowed to go through it. Let me jump forward just a minute here to this figure 4-3. This is a cutaway of the cell, cutaway of the cell membrane. It is a bilipid membrane, a bilipid structure. Lipid here, bilipid structure. This is the outside of the cell. This is the inside of the cell. So cytoplasm here, outside world there, in this case extracellular fluid. You'll notice that there are these proteins that span the membrane from the inside to the outside. They give you a nice little cutaway of one here. And you can see there's another one over here, and there's one over there, and then you have these other proteins with carbohydrates sticking out of it. That's proteoglycans or glycoproteins sticking out of that cell, sticking out of the membrane. That's because that wall that goes around the cell is a lot like a wall that goes around a house. And we have walls going around our house to keep things outside that we want to keep outside and keep things inside that we want to keep inside. That's why we live where we do, with those walls and roof around our house. However, we have to have the ability to get some things in and out. If there was no ventilation in your house, if it was solid walls like a bank vault, after a while you would run out of air and die. So in your house you're going to have things like windows, but those windows are going to be kind of small. They won't allow for things like a car to come through. And they'll have a screen that'll keep out flies and bees and birds and other things. Maybe not really tiny insects, but it'll allow oxygen to come into the house. And it'll allow that carbon dioxide that you breathe out to go out of the house. You've heard of ventilating a patient, right? And you've also seen on a can of paint, using a well-ventilated room. Bad air out, good air in. In that house, though, with that screen, As long as it's very small, tiny, tiny particle, then it can go through at its leisure. So if it's a very, very small particle, it can go through here, or it can go out that way. If there's more small particles in here compared to out there, some are going to leave. If there's more out here compared to in there, some are going to go in. At their leisure, if they're small enough, they can fit through that space, no problem. But sometimes we want to get things into our house that are bigger, like a refrigerator or a sofa, or a car, if you have a house that has an attached garage. So then you have a great big door, right? This is a door that you can open and close as long as you have the remote, as long as you have the key code, as long as you have a key, as long as you have something that is not easily to maneuver around, I guess. Key code, I think, is the best example. You ever see, a garage door, you walk over, you punch in the key code, the door goes up, punch it in, the door goes down. Same idea. As long as something has the code, if it's large and wants to get through here, it goes to the protein that has the door on it. Locks in its code, door opens up, it moves in. Door closes, or vice versa, goes out. So we can get things in and out of a cell. If it's really, really small, it'll come in and out at its leisure. If it's larger, only if it has the right code. And what we'll end up with is more or less of those things inside of the cell as compared to as they were previous. If we created a lot of something and we moved some out, now we have less than what we started with. So we made a change in the cell. If we have a lot of little things coming in, there were less before, now there's more, we've made a change inside of the cell as things have come through. But what if, let's see, we can make a change inside of a cell in some cases where nothing actually goes through at all except for a message. And if you've ever lived in a mansion or an apartment that has one of those intercom systems, somebody knocks on the door and you go to the intercom, you say, "Who is it?" And they say, "Pizza guy." And you say, "Bring it around to the back door." There must be at least 2 doors. Or your neighbor comes over, knocks on the, and rings the buzzer, and you go up to the intercom and say, "Who is it?" And they say, "This is your neighbor. Your music is too loud. Would you mind turning it down?" And because you are a friendly, compliant neighbor, you go over and turn your stereo down. You created a change inside, right? Something changed. Something became different. But what actually moved from outside inside? Just a message. This works the same way. Very, very small particles like oxygen molecules go right through here. Fat, like steroid hormones, they just go right through the membrane. That's easy because most of that membrane actually loves fats. Most of that membrane loves fats. Most of it loves fats. So if fat loves fat, remember the fat on top of that water? Whoosh, try to stay together. If it's very, very large, like that glucose molecule, insulin brings it over and says, "Here's the code," opens the door, glucose goes in. Or in some cases, all we do is get a message through. See that in the second messenger systems. But we can do that, we can make a change inside of the cell. That's how we cross the membrane. Now, if you look at that structure of that membrane, that picture of that membrane, you'll notice if you were on the outside, if you were just standing over here and looking at this cell, you would see that this has one of these little lumpy things here sticking out with some carbohydrate stuck to it. And then one of these circle ones here with the tunnel through, and then another one of these with the carbohydrates, and another one with the carbohydrates. You would start to see a pattern. These are sticking out of here with a purpose. Since I'm right here. You would start to see a pattern. you would see cells with these little things sticking out of them. You see how this group all looks the same? Well, what is wrong with this picture? We have one cell that does not look like the others. We have one cell that definitely doesn't look right. This is what our immune system does all day long. It sees this cell and says, yep, that's correct. Yep, that's correct. Yep, that one's right. Yep, that one's right. They all look the same. Yep, that one's correct. And then they see this, and they say, uh-oh, now we've got a problem. This isn't right. This doesn't belong. We have to destroy it. All based on these. Every one of us has a unique pattern of these proteins, these carbohydrates, sticking out of our cells. They're unique to all of us. None of us are alike. Now, this is a big difference, right? You can see that one easily. What if the difference wasn't as obvious? Would the body attack it? Yeah. Eventually, it would attack it. But it wouldn't attack it heavily. It would be a light attack. You see, the bigger the difference in how the cells look, the bigger the attack. Smaller difference, smaller the attack. You ever hear of anybody getting an organ transplant? Before they get that kidney transplant, they have to find somebody who matches, right? Well, they're not going to find a perfect match. That's impossible. But what they will find is someone who is close. If we put a kidney in that patient and those cells look this different, it's going to be attacked that fast. That fast, literally. It will be attacked that fast. Which means moments later the kidney is going to be useless. If it looks like this, then it's not going to be as attacked as heavily. So now we have to put the patient on immunosuppressant drugs for the rest of their life. We have to suppress their immune system. We couldn't put them on a dose big enough to suppress the immune system against that. That is too different. It's going to get destroyed, it's going to be useless. So we're going to put them on, we're going to find something that is very, very close and put them on immunosuppressant drugs. Big concept, because we'll see this again later in hematology. We'll see this again in immunology. The bigger the difference, the bigger the attack. Based on those little proteins that are sticking out. Very simple. Cell membrane is the boundary, the protective covering. It allows things into and out. It is, well, not thick at all. Maybe 10 millionths of an inch thick. Why they chose inch, I don't know. Cell membranes are selectively permeable. You'll hear me use the term selectively permeable and semi-permeable interchangeably. Cell membrane is made of that phospholipid bilayer. The brown head, the two tails, prevents polar hydrophilic molecules from passing through the membrane, but does allow those nice cholesterol-based molecules to spawn through, the hydrophobic ones. Proteins in cell membrane identification markers are identified as coming from a certain person. Is that what I just said right here? Those proteins that are sticking out? are markers. And there are channels and gates, and those channels and gates, of course, are made of, and this is going to surprise you, proteins. Shouldn't be a surprise at this point. This class should be renamed the protein class, because you're going to hear so much about it. How do we get things into or out of a cell? Transport. Here's a quick way to define active transport. Anytime you take an exam, I don't care if it's in this class or a certification exam, you go into medical school, anytime you take an exam and that exam starts to read blah, 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 needs energy. Blah, 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 requires energy. Blah, blah, requires ATP. Anytime you see something that needs energy, needs ATP, the very first thing your brain needs to do is switch on active transport. See, this is active transport. Anytime you see it requires energy, requires ATP, needs that from one side of the membrane to the other, your brain should automatically start thinking active transport, active transport, active transport. And then, of course, when you think active transport, you got to go back to thinking energy, energy, energy. Active transport, energy, energy, active transport. Which means if a patient is in a low energy state, you have a difficult time with that energy, which means you have a difficult time with that active transport. Which means if we're trying to push something against their concentration gradient, we're going to have a difficult time with that. All right, moving things in and out of the cell can be done in two broad ways. Passive transport requires no energy input. It requires no energy input. Passive transport requires no energy input. In order to move something, how do you move something without energy? How do you make something move 100 feet, 50 feet, 2 feet, without using any energy? Well, like that, right? Didn't use energy, what did I use? I used a force. It's gravity. But there are other ways, too, not just gravity. Passive transport can be divided into these types: diffusion, osmosis, filtration, and facilitated diffusion. If you are at all asleep right now, or if your brain is drifting off, does anyone want to take a few minutes? Take a minute break or 5-minute break or anything? Take a few minutes, because this stuff right here is